The purpose of this lab is to explore how Earth's gravitational force and the force of air drag affect an object's motion. To do this, we can film an object that would fall slower than a rock, analyze that object in Tracker, create corresponding virtual models, and then compare the results. In the previous lab, we learned Newton's second law, which states that the final velocity of an object is equal to the initial velocity plus the net force divided by the mass of the object times the change in time. However, in this lab, we are dealing with a non-zero net force, and therefore the object has acceleration. The net force in this case is the force of gravity plus the force of air drag. The force of gravity, otherwise known as weight, is calculated by multiplying the mass of the object times the gravitational constant, which for the purposes of this lab we will assume to be 9.8 meters cubed divided by seconds squared times kilograms. The drag force is directly proportional to the square of the object's velocity and is found by multiplying a constant by the velocity squared. Notice the negative sign. This indicates that this force is opposite the velocity of the object and will therefore slow it down. The reason we are using the velocity squared instead of just the velocity is because the model predicted by just velocity is viscous drag, which deals with liquids. This equation models turbulent drag, which is applicable to our present situation. In my model, I filmed myself dropping a crumpled sheet of paper from above my head and analyzed it in Tracker. I calibrated the length scale with my height, which is about 1.73 meters, and set my axes so that the paper fell in the negative y direction and with the origin as the initial center of the ball of paper. And for 19 frames, track the center of the object in order to gather data for a graph. As you can see, this produced a line plot with an increasingly negative slope, indicating that the paper is accelerating in the negative y direction. Although the paper moves slightly in the x direction, it is very minuscule, and we will neglect this since we are solely focusing on motion in the y direction. I then coded in VPython a model of the object affected only by gravity, setting the drag force constant as 0 to achieve this. I entered the ball's mass, the ball's initial position, and velocity, which I defined as 0 since I dropped the paper from rest, assigned a gravitational constant, a unit vector, and defined the weight of the object off of these values. I then set the net force equal to only the weight. Finally, I drew in arrows in order to identify the forces on the object, in this case only gravity. The result is as follows. As you can see, gravity is the only force acting on the object in the negative y direction. I then created another model that accounted for air drag. In order to do this, I had to define a proportionality constant, b. This is virtually impossible to do mathematically, which is a reason why we do this lab. In order to do this, I tried out different constants until the final position of my model matched that of my observed. The result is as follows. Notice how the drag force is up and gradually gets larger as the magnitude of velocity increases. Finally, I put all of my data into a spreadsheet and created a line chart. As you can see, my model without drag clearly overpredicted my object's actual motion, whereas my model with the drag predicted my object's motion very accurately. There is some error, probably due to having to estimate the center of the object in Tracker when at times it was a blur, but overall it is a good prediction, which clearly shows the existence of a drag force. Because my first model has no force working against gravity, the object would accelerate downwards until it experienced another force. My drag force model, on the other hand, experiences a force against it that increases in magnitude as velocity magnitude increases, which limits the speed to a certain value, called the terminal velocity. In conclusion, the drag force opposing gravity limits limits an object to a terminal velocity. Initially, gravity would accelerate the object downwards, but this increase in velocity magnitude would result in an increase of the opposing force magnitude. Once the object reaches a certain velocity, the drag force would equal the gravitational force in magnitude, resulting in a net force of 0. As a result, we can see by Newton's second law that the object would move with constant velocity. An object thrown downwards would not have a higher terminal velocity. Since throwing the object would increase the object's initial velocity, the drag force magnitude would be proportionally larger than it would be if the object started at rest, and would still increase till the same terminal velocity is reached. Thus, the object would have the same terminal velocity but would reach it in less time. Thanks for watching.